Hello, we are the Spartan Superway Boogie Chassis Team, and this is our team. First, I'll hand it off to Andrew to introduce Rapid Transport Networks.
The Spartan Superway Project is a rapid transport network that plans to revamp the public transportation system to fit our modern time. The way the Spartan Superway Project plans to accomplish this is by implementing various new features to the transportation system. The project goal overall is to have independent pods suspended in the air that are autonomously controlled and powered by renewable energy from solar panels. This is exactly what the picture on the left is aiming to show. What differentiates the Spartan Superway from other current public transportation systems are key characteristics such as offline stations, which can be used at times that are convenient for users in order to accommodate for all people, similarly to what the picture on the right is trying to depict. Non-stop traveling, allowing easy, quick, and convenient trips for busy commuters. Always on-demand pods, making sure that a pod is available for any consumer to use at any time. Solar-powered project using electricity, which has many benefits relating to the environment. Strategically placed guideways that ensures a familiar and exclusive path to what the pods will travel on. The Spartan Superway project is made up of 4 teams. The Boogie Chassis specifically, however, holds a high importance and is vital in many various industries. The chassis' role is to be the main support system of a vehicle. It should be able to withstand the vibrations and forces in dynamic conditions. The picture on the left is a chassis that is used for cars and which needs to operate for long and rough conditions. If the chassis has issues or doesn't work, the car simply won't move. Comparing this to our chassis, we serve as the base of the movable pod as seen on the right picture within the circle shown. As you can see, the chassis is essentially the skeleton of a vehicle, which gives way to the importance of our role as a Boogie Chassis team. Our particular project is to create a Boogie chassis that carries its energy supply and operates under wireless control while withstanding a designated load on the scale model guideway. More specific tasks can be divided up into 4 categories such as mechanical design, sensor, power systems, and suspension. These 4 categories that the Boogie Chassis project is separated in can ultimately help achieve the goals that are embedded with the Spartan Superway project, such as being autonomously controlled and solar powered. The picture on the left showing a Boogie chassis on a guideway with a carriage suspended below is the ideal end goal for our project. The picture on the right depicts the mechanical design and components that go into a Boogie chassis. These components are important to use when designing our Boogie, so it operates towards completing our 4 categories of tasks stated beforehand. To continue forward with the problem that the Boogie team has, it is important that while we work on our design, we always keep in mind other teams' dependencies and requests. This ensures that the team can integrate together smoothly and that the project as a whole goes soundly. Now, I will introduce Max to bring up the mechanical team slides.
We will now get into the progress that we've made on the mechanical team. There are still a few systems which need to be implemented to fulfill design specifications. A 100-pound load will be applied to the connection point from the chassis to the carriage. Thus, a strong connection to the carriage must be designed, and a suspension system to ensure smooth rides for passengers. The lateral wheels on the bottom of the bogie make up much of the area available to mount the carriage, which poses a challenge. After doing some research, we found train cars will use both primary suspension consisting of springs and dampers, as well as secondary system involving an air spring system to further minimize vibrations. Using inspiration from other systems such as these is helpful when considering suspension for the Superway bogie, but other techniques may need to be implemented due to the small scale of the bogie. Spatial management is a constant focus in this project. We are currently working to ensure each programmable board and sensor will fit nicely on the bogie. The components of the system must also be easily accessible and arranged so that a minimal amount of wiring is needed. There should be enough room above the electronic components to use tools in case there's need to remove or replace certain features. In addition, the height of the switch arm and bogie need to match so that the connection with the boss can be achieved on the track. Next, I'll let Michael talk about the bogie chassis design iterations.
Here is a visual timeline of how our Boogie chassis concept evolved over time. The current concept version 2 is similar to version 1, but with changes such as removed flanges, an updated suspension system, an updated cage/housing for the electronics with accommodations for switch arm, new lateral wheel stabilizers to account for inconsistencies on turns on the track, and a carriage attachment design that has yet to make a full implementation. Now I'll hand it off to Christian to introduce an updated suspension system.
In order to ensure a smooth ride, we designed a suspension system consisting of a compression spring and 2 dampeners on each side of the bogie. The spring, which is outlined in orange, will provide compressive support, and the dampers are placed on each side of the spring and are outlined in purple. While designing the suspension system, we considered several configurations involving pre-assembled shocks as well as self-absorbing dampers that are available on the market, but many of these considerations were deemed unnecessary for the application. We ultimately settled on this configuration as it was determined to be the most elegant, simple, and economical solution for the amount of vibrations anticipated at this scale. The dampers utilized are polyurethane skateboard bushings that are available in a variety of sizes, shapes, and hardnesses and are very cost effective. They will be placed on each side of the spring to absorb any excess vibration generated by the spring and uneven track surfaces. Lastly, the final design will feature a spring whose tension will be adjustable by simply changing the spring length or by utilizing a set screw through the center of the spring. Next, Andrew will discuss the modifications for the bogie cage.
In order to properly accommodate for switch arm's design, a cage was placed on top of our bogie chassis shown on the picture. The job of the cage is to be able to support and act as a base for placement of the switch arm. The base will have a width of 9.81 inches illustrated by the green line and a length along the chassis of 11.26 inches illustrated by the purple line. The switch arm team will be able to comfortably put their design on top of our bogie with room for adjustments as well from their side and our side if needed. The height of the cage was decided to be 3.0 inches illustrated by the orange line. Inside the cage, we will be placing all of our sensors and battery in one snug place, and we needed to be able to clear the tallest object within the cage. The tallest object was the battery, approximately at 2.25 inches extruded off the chassis. Adding a tolerance to this and also accommodating for our sensor team, we felt 3 inches was the best way to be able to have an easy access to the sensors, battery, and wiring. I will now introduce Max to discuss modifications to the initial cage design.
The considerations that went into the housing design involved the space management, easy access for modifications, and protection of electrical components. With the top part of the housing being just for switch arm, that left lots of space for them to mount the switch arm as well as leave some extra space for possible sensors that needed full field of view. In addition, side panels were implemented in order to prevent dust and debris from getting into the electronic components, which could result in damaged equipment. In addition, the design was adjusted to utilize an easily removable lid so that the electrical team can modify the electronics from above without having to reach in from the side and easily use tools to change components. Lastly, a hole was also put in the side of that panel in order to allow the emitter for the track team to reach the receiver on the track. Next, I'll let Michael talk about the lateral stability.
Alongside the development of the main lateral wheel stabilizers is our alternative second design. For this secondary design, the design philosophy is to create lateral wheel stabilizers with more space in the center to accommodate for the carriage attachment that will simulate the maximum 100-pound point load. On the left, you can see a static representation of how the stabilizers can adjust to inconsistencies on the track. Spring's tension will allow the wheels to move in an arc and theoretically conform back to its original position. The design has been exaggerated to show the range of motion, but can be adjusted to ensure that the wheels don't collide when making contact with the track. However, the only downside to this design is that the concept uses more materials than the current lateral wheel stabilizer design. And next, Carlos will go more in depth with the current design.
The current design for the lateral wheel stabilizers consists of a link and tension spring that will allow the wheels to always exert an outward force on the track to maintain full contact as the track dimensions change due to inconsistencies. As the width on the track decreases, the wheels will go inward in the direction of the yellow arrow and rotate the link. As the link rotates counterclockwise, it will pull on the string in the direction of the purple arrow and adding tension to the spring. The spring will then want to compress and return to its natural length, thus force the wheels to return to their initial position as the track widens. The max dimensions on the bogie are labeled in the image. It can be seen that the bogie has a max dimension of 16.83 inches in length, a max dimension of 4.38 inches in height, and a max dimension of 12.75 inches in width. The dimensions are subject to change given if we need to take any new constraints into consideration when integrating with other systems such as the track and switch arm. However, the main subsystems that make up the bogie are solidified. The main components incorporated into the bogie design consist of the main bogie frame that will contain all the electrical components, such as the sensors and power system, in addition to the switch arm. Second, we have incorporated a housing that will protect the electrical components and meet the demand of the space required for the switch arm. Third, we have an axle that is fixed to the bogie chassis by an axle clamp, hinge, dowel pin, and bearing that will allow the components to rotate as the bogie oscillates. Fourth, the suspension system is comprised of the suspension link that will hold the spring and dampers to counteract the vibrations acted on our bogie. Fifth, we have lateral wheel stabilizers that will allow the wheels to exert an outward force and maintain the bogie on track. Lastly, we have Mqtt hub motors that will drive the bogie. The main components on the bogie can be clearly seen in the animation. An exploding view was performed to demonstrate the relationship between each component and the order of which the bogie is to be disassembled and assembled. To begin, the hub motors are to be removed by unscrewing this cap nut and removing the suspension system. Next, the axle can be removed from the bogie by detaching the dowel pin from the hinge. Next, the stabilizing wheel mechanism can be disassembled by unscrewing the bolt from the chassis and linked to ultimately remove the spring. Lastly, the encasing can be removed to access the electrical components. Next, Max will explain the carriage attachment developed.
The carriage is where passengers of the Spartan Superway system will be sitting during transportation. The connection between this and the chassis needs to be sufficient to support a 100-pound load and be mounted so that it does not interfere with the lateral stabilizers on the bottom of the chassis. To do this, L brackets with machine screws will be used to attach the square pipes to the load representing the carriage. The length of these pipes is 6 inches, and the other dimensions are 1 by 1. Next, here's Carlos to talk about the stresses in the bogie.
Using Abacus, the finite element analysis for the aluminum chassis was performed to simulate a distributed load of 100 pounds at 6 inches from the center of the bottom surface. It was determined through the simulation that the most amount of stress will be located at the corner of the bottom extrusions of the lower surface with a maximum Mises stress of 102.9 psi. The results have determined that the bogie specification should withstand the forces exerted on the frame. Next, Devin will develop on the electrical side of the bogie.
The overall design for the bogie's electrical portion is comprised of a Lowland D32 microcontroller that will be the central hub that delivers commands to the motors, collects data from sensors, and communicates with other teams such as IoT and track. We will use a LiPo battery and a power distribution board to deliver power to all electrical components. The gyroscope accelerometer combo will collect data on bogie tilt as well as accelerations and decelerations. All data will then be sent to IoT with Mqtt Protocol. Next, Alex will talk about the circuit design more in depth.
Right, so from last presentation, we've created a schematic to get a better bead on sort of where all the wires and powering is going to go. We're using a combination of voltage boosters, buck converters, and voltage dividers in order to supply adequate power to the system. We're using Z diodes in order to protect certain circuits, but because Z diodes are known to fail, we may be using capacitors later on in order to protect them if the transient responses due to the switch arm actuation are heavier than we anticipate. The boost converter is required because the battery only supplies 22.2 volts, and we need around 24 to 36 volts in order to adequately supply power to the motors. Because we cannot constrain the amperage because amps are more reliant on torque, we needed to use a boost converter that supplied enough voltage as well as supplying enough amps as well. The following boost converter was selected. Finally, we needed a buck converter to ensure that the smaller, lower voltage components were able to be adequately supplied. We're using this buck converter. A quick load calc is done above to ensure that the buck converter can supply a full load to pretty much all the other small, low amp devices. As you can see, it's well within spec, so this should be no problem. Now on to Hussein to discuss the motor methods and API.
Our VSC board needs to communicate with the motor using UART and be able to relay the PWM value as well as obtain current values such as brake current, input current, motor current, as well as duty cycle. After understanding the API that was built by the core team and applying existing motor control functions, we can command the speed of the bogie while having it relay the parameters required. Going forward, the integration of code to motors needs to be performed and troubleshot based on our circuit schematic to obtain any relay signals efficiently, as well as implement control loops for different scenarios being faced by the bogie, such as braking, slowing down before switching or turn. Next, we will talk about the Mqtt protocol and how that helps us communicate with the different teams and IoT. To establish a communication protocol between the sensors and IoT, Mqtt protocol is going to be used. The base for constructing the architecture of an Mqtt server and connecting has already been set up in the API provided by the core team. More in-depth understanding of the code and Mqtt protocol is required to successfully communicate the sensors used in the system. The idea behind the Mqtt protocol is to either use the server set up by the Riot team on a computer and communicate this data based on the subscriber's requirement. Now, Devin will talk about tilt detection using an IMU.
For the IMU, the LSM9DS1 was chosen. We will implement one on the front and one on the rear of the bogie for more accurate data collection of tilt and acceleration. The board will be used to ensure that the bogie does not exceed 5 degrees of tilt or half a G of acceleration. This board was chosen for its low cost and functional specs. This board is small and lightweight, weighing only a couple grams, with a size of 1 inch by 0.7 inches. It accepts 1.9 to 3.6 volts, has a resolution of 16 bits, and can communicate through I2C and SPI. For our applications, we will use I2C connections to reduce the number of wires. We will also implement a complementary filter for the accelerometer gyroscope. The gyroscope collects data at a faster rate compared to the accelerometer, but is more prone to drift over time. The benefits of the accelerometer is that there is no drift and it retains its accuracy for static situations. However, it suffers at high speed situations. A complementary filter will allow for a compromise in speed and accuracy, which will help yield better data collection while the bogie is running. On the right side of the slide shows the basic principles of how the filter works. Essentially, a certain percentage of data will be taken from the accelerometer and the rest will be taken from the gyroscope. On the left side is the code for collecting data from the board and implementing the filter. Jake will now talk about object avoidance.
Our plan is still to use LiDAR to detect track anomalies and to localize the bogie. We've decided to use the Velodyne VLP16 instead of the SlamTech A1 because we were recently lent one to use by Professor Perez. The VLP16 is well documented and commonly used in industry. The system has a 360-degree view and is more accurate than any of the previous systems we had. It also has a vertical field of view. It can see 14.5 degrees from center and negative 14.5 degrees from center. It has a vertical resolution of 2 degrees and a horizontal resolution of 0.1 to 0.4 degrees. It has a rotation rate of 5 to 20 hertz, and it's also IP67 environmental protection. Our plan is to use the top half of its field of view to localize the bogie on the track. We will also use the bottom half of the field of view for object detection. This will make it much easier to code. The upward-facing portion of the LiDAR will have little to no interference from objects on the track. We can see in this diagram here how the localization beams and the object detection beams will be used. The closest distance that we can detect an object is 1.5 feet. This is a factor of the height of the LiDAR and the angle of the lowest beam. We are still planning on using SLAM for localization. With the 3D capabilities of LiDAR, this system will have much more data to use and as a result will be more accurate. To power the algorithms we will use for the LiDAR, we initially chose the Raspberry Pi Zero. Since we have changed the LiDAR to a 3D LiDAR, we will also have to change the board that runs the algorithm. We currently have a Raspberry Pi 4 that we will test our implementation of SLAM on. Theoretically, this board should be sufficient to run our algorithm. In the case that it is not, we will have to choose a more powerful board. This will likely be a Jetson TX2, which the VLP16 and SLAM is known to work perfectly on. Now let me pass it on to Alex to talk about dependencies and contingencies.
Right, so from last presentation, we've actually had a couple dependencies marked off our list. We're still waiting on the total weight of the switch arm system in order to just ensure that our motors will adequately move our whole bogie. We're also trying to get a final answer, and I think we're pretty close to this, on the sensors, boards, and motor switching arm that the switch arm is using. And then finally, we're waiting on the charge station implementation to figure out how they want to charge the battery. And if so, that's going to factor where the battery is actually going to be on the housing. And if that's not possible, then we're just going to ensure that the battery can be easily removed to charge outside of the bogie. And I'm going to pass it on to Michael G to discuss the Gantt chart.
This is the current team Gantt chart. Based on the number of completed tasks, we still expect to finish on time. Next, I'll go more in depth on the progress of the mechanical team. During the time of this presentation, there are some tasks we have completed and are working towards. On the mechanical team, we're collectively on track with the updated CAD design of the Boogie Chassis. As we approach the end of November and early December, we'll have an official design that will be reviewed for further analysis and testing. We are currently need to conduct further testing on the lateral wheel stabilizers. For simulation testing, we've been using the program Abacus. From now to the end of the semester, the mechanical team will shift focus to designing and analyzing a carriage attachment for the point load. And next, I'll hand it off to Devin for the Gantt chart for electrical team.
On the electrical side, we have finished motor and battery sizing, choosing ESC, selecting proximity sensor and IMU, and programming for the IMU and ESC. Moving forward, our focus will be on the proximity sensor programming, designing the power distribution board, and continuing on integrating with other teams. Overall, we are on schedule to complete all objectives on time. Thank you for listening, and that concludes our presentation. We will now take any questions.